In April 2026, after 22 years of development, India announced that its Kalpakkam prototype fast breeder reactor had finally achieved criticality, the moment a nuclear core sustains its own chain reaction. These reactors are an engineering paradox. By design, they are built to produce more fuel than they consume. The United States, UK, Germany, and Japan spent a combined $50 billion trying to master this technology before abandoning it. The difficulty lies in the coolant, liquid sodium. It catches fire instantly upon contact with air and explodes if it touches water. Hazards that led to a massive fire at Japan's Manju plant just a year after it went critical. Despite these risks, Indian engineers completed their project for less than $1 billion, a fraction of the cost spent on the West's failed attempts. This wasn't a pursuit of prestige. For India, mastering this machine is the only way to overcome a geographic reality that threatens its long-term growth. India faces a massive energy deficit. It has 1.4 billion people and a rapidly industrializing economy, yet it possesses almost no domestic reserves of standard uranium. However, the coastlines of Kerala and Tamil Nadu hold a hidden advantage. These black sands contain roughly 25% of the world's thorium. The problem is that thorium is naturally inert. You cannot simply put it in a reactor and start a fire. It will not sustain a nuclear reaction on its own. To solve this, India is executing a 70-year, 3-stage master plan designed to tap into the energy potential of those coastal sands. To make that sand burn, India had to invent a cascading chain reaction where the waste produced today becomes the vital ignition fuel for the next generation of reactors. Stage 1 standard reactors burn natural uranium for electricity, leaving a plutonium byproduct. This plutonium feeds the new Stage 2 reactor alongside depleted uranium. Here, breeding transmutes depleted uranium into more plutonium, creating a continuous, expanding loop of fuel. The Kalpakkam reactor isn't just a power plant. It is an elemental forge designed to manufacture the specific spark required for the plan's final stage. In the next phase, engineers wrap the Stage 2 reactor core in a blanket made of the inert thorium gathered from the beaches. As the core pulses, radiation bombards the thorium blanket, transforming it into uranium-233. This U-233 moves into Stage 3 reactors, burning alongside raw thorium to create a self-sustaining cycle. With vast thorium supplies, this cycle can power India for centuries. Stage 2 was never the end of the journey. It was the technical bridge required to achieve a permanent domestic energy monopoly. With the Kalpakkam reactor going critical, India has crossed the most difficult technical hurdle in its 70-year timeline. However, this success has strategic implications. Because Stage 2 is effectively a plutonium factory, it inherently provides dual-use capabilities. This single reactor has the capacity to produce 150 kilograms of weapons-grade plutonium every year. That is enough for roughly 30 to 40 nuclear warheads as a byproduct of its energy production. While the official focus remains on civilian power, this milestone ensures that India's strategic deterrence is fueled by the same domestic cycle that powers its cities. This entire path was mapped out by Dr. Homi Bhabha, who envisioned the system in the shadow of the first atomic age. Bhabha convinced the government that for a civilization to survive and grow, it must control its own energy sources, rather than relying on international markets. The program survived decades of shifting policy, economic hardship, and global sanctions because the logic of energy independence remained constant. Now, the machine is running. By learning to burn the sand on its own shores, India has transitioned from a country chasing Western science to one that owns its energy future.